All right, 8.3 is the synthesis of alcohols. We've only learned, well, we've learned two reactions already. So this is review, two reactions. One is, well, I guess technically three, but one is you add acid and water, and you get the Markovnikov alcohol. You add it to a double bond. Oh, that is incorrect. The OH goes, Markovnikov goes to the more substituted position. Sorry about that. All right, that is the Markovnikov product. We have learned the anti-Markovnikov, which is you add BH3 and you add H2O2 and sodium hydroxide, and you can get the OH on the least substituted position. All right, those are two reactions. The other one is SN1 or SN2. SN2/SN1. Take some sort of alkyl halide. I'm just going to put X and add sodium hydroxide, or add hydroxide to it, and you can make an alcohol out of that. So those are the three ways. One is Markovnikov, one's anti-Markovnikov, one is wherever your halogen is, that's where your OH goes. Okay? In this chapter, we're going to learn how to make an alcohol by a reduction. Okay, it's a new reaction. Reduction means adding hydrogen to carbon. Remember, oxidation, reduction in this class is very simple. Reduction, adding hydrogen to carbon, or another way of looking at it is losing oxygen on carbon. All right, or less oxygen bonds. Not necessarily losing oxygen, but less bonds. So to give you an example, let's say we just take a generic ketone. We're going to add a reducing agent. That means we're going to be adding hydrogen. Okay, the hydrogen we're going to be adding is a hydride. It's H negative. So hydrogen has a lone pair on it. And what happens is it adds, and you lose a bond to oxygen, and you form an alcohol. So notice we go from 2 bonds to oxygen to 1 bond to oxygen. Okay, and this hydrogen with a lone pair, let me write a little bit better here. This is called hydride. Okay, we're going to be adding a reducing agent. All right, and there are 2 reducing agents that we add. All right, one is called sodium borohydride, NaBH4. It stands for sodium borohydride. You don't have to remember the name of it, but you might hear me say it. The other one is lithium aluminum hydride. These are hydrides. Lithium aluminum hydride. Lithium aluminum hydride. Okay. For short, people call it LAH. There is no short for sodium borohydride, but for short, lithium aluminum hydride, they call it LAH. Sodium borohydride is a mild reducing agent. Okay. It's mild, easy to handle, it's cheap. Okay. LAH, or lithium aluminum hydride, is exact opposite. It's a very strong hydriding agent. It's a little bit more challenging to handle, so hard to handle. And it's a little bit more expensive. It's also, there we go. It's also quite explosive. All right, lithium aluminum hydride, you can actually, what you do is it's dissolved in a solvent, in a liquid, and you pull it, and you take a syringe and you pull it up in a syringe, and what you can actually do, what we used to do in grad school, we used to actually squirt it out of the syringe as hard as we can, and as soon as the lithium aluminum hydride would react with the oxygen in the air, it actually would ignite, and you get this stream of fire across the room. It wasn't really safe, but pretty cool to watch. Okay, that's a very strong reducing agent. Sodium borohydride is a white solid, and you can weigh it out in the air. It does not react with oxygen. It just strictly reacts with carbonyls. The only problem is that sodium borohydride only reduces or only reacts with ketones and aldehydes. All right. But what if you have a carboxylic acid? What if you have an ester and you want to reduce those? Well, you have to use a much more powerful reducing agent, and that is where lithium aluminum hydride comes in. Lithium aluminum hydride reduces everything. Okay, it just can't spell today. It reduces. Let me write that over. It reduces ketones and aldehydes. But it also reduces carboxylic acids and esters. Okay, so LAH is much stronger. It reduces everything. Sodium borohydride just reduces ketones and aldehydes. So why would you even have sodium borohydride? Well, like I said, sodium borohydride is safer to use. Okay, if I have a ketone and I want to reduce it, I'm not going to use LAH. It's not that safe to actually use, and I would rather use something much more mild and easier to use. So that's why I would use sodium borohydride. If I have a carboxylic acid, I got to reduce it. Then I have to use LAH. It's like, why use a nuclear bomb if I'm trying to kill a fly, right? There's no reason to use a nuclear bomb to kill a fly. Just use a fly swatter. Okay, it's kind of the same analogy. If I can use a fly swatter, sodium borohydride, there's no reason to use a nuclear bomb, LAH. Okay, so what the reaction is, these reactions are always two steps. The first step is adding your hydride agent. Your second step, as you'll see in the reaction, is working the reaction up in acid. Acid workup is what it's called, because you'll form an ion and then you have to protonate your negative charge. Okay, so let's just take a simple reaction. So let's take an aldehyde, add sodium. So here's the reaction: sodium borohydride. And then the second step is adding acid. And your final product, I'm going to write in all the hydrogens on this carbon just to kind of show you. Okay, so look at sodium borohydride and lithium aluminum hydride as if it was an H negative. That's what you basically should look at. It's a very complicated structure. The sodium and the boron and water eventually all hook up and it turns into a salt and you just wash it away. That's what happens to the boron. But basically one of these hydrogens gets added onto here and it breaks your pi bond. All right, so let's actually look at a mechanism. So again, look at sodium borohydride as if it was a hydride. All right, so what it does is the lone pairs come in, your hydrogen's acting as a nucleophile, and kicks up your lone pairs, and you form O negative H plus your H just added. Your second step is adding acid, H plus, and that's because your oxygen now can protonate from the acid. So that's why it's a two-step process. One hydrogen to do the reducing, the other hydrogen to protonate your O negative. Okay? Another example, let's look at a ketone. So if you have a ketone, add sodium borohydride, and then add H plus, and you can get the alcohol. I'm not going to write the hydrogen in, but we know the hydrogen added. You can do the same thing with LAH. Okay, you can do the same reaction. So let's take the the aldehyde, add LAH or lithium aluminum hydride, add this. You do a nuclear bomb. Flames are going everywhere, but you still get the same product. Okay. However, if you have an acid, carboxylic acid, or an ester, you can only use LAH. Okay. So if you have a carboxylic acid, you add LAH and acid, and you get an OH. All right. This part of it, the OH part of it, eventually comes off as water. Let's kind of look at a mechanism. Okay. Hydride is H negative. This comes in, that goes up. You form O negative, you have an OH, and you have your H. What happens is these lone pairs pop back down and kick out the OH. So you actually form an aldehyde plus hydroxide. And then what happens is another equivalent of hydride comes in, because now you have an aldehyde, it's very reactive, deprotonates, and you get your O negative plus your two hydrogens. So technically, you're always adding two hydrides. Okay, so you really have to add two equivalents of LAH. You don't write that because you always put excess LAH, but you don't have to write the two equivalents. Okay, and then the second step is you add acid to it. I don't have room here, I'm running out. You add acid to protonate your OH, and it protonates the hydroxide that you form. So you form your water and your alcohol. Okay, so in this case, it's a little different. It's a two-step process rather than a one-step process. On the next page, I'll do a ester example. Okay, so OCH3, same thing. You have add LAH and acid. You technically add it twice, so you form an OH. And in this case, rather than adding water, you form this compound, which comes from this group leaving. So what you should do for practice is, why don't you go through the mechanism for the ester? Same type of thing. I'm going to put it on pause. Why don't you put it on pause and go through the mechanism? And when you come back, I'll have the mechanism all drawn out for you. All right, so here's the mechanism. You can see that the hydride comes in, all right, attacks the carbonyl on your ester, kicks up the pi bond, just like before. Your O negative forms, that pops back down and kicks out your OCH3. That's where your methanol is going to come from. And then you form the aldehyde. All right. Then your hydride, another equivalent of hydride, comes in, does the same thing, forms the O negative. This time there's nothing to leave, so you add the acid and it protonates your O negative. Okay? So that's the difference between LAH and sodium borohydride. Just depending on what you have, you can use either one. So kind of a summary. Okay? So aldehydes, ketones, sodium borohydride is preferred, but you can use LAH. The reason is because sodium borohydride is safer. Aldehydes, ketones, carboxylic acids, esters, LAH can do it all. All right? Sodium borohydride cannot reduce carboxylic acids or esters. Okay?